The first bulletin said, magnitude 7, 0, 258 kilometers off the coast. 45 minutes later, the number changed. The location changed. And buried inside that correction was a detail scientists had been quietly watching for since June, a stretch of fault that hasn't moved since 1918. This is what that earthquake actually revealed. It happened at 14 minutes past noon, Philippine Standard Time, on a Wednesday in early August. A strong earthquake struck offshore in the southern Philippines, off the southern tip of Mindanao, in a stretch of ocean that had already been under close watch for 2 months by the time the shaking started. Within minutes, the Philippine Institute of Volcanology and Seismology, the agency everyone in the region simply calls PHIVOLCS, issued its first bulletin. Their first read put the magnitude at 7, 0, with an epicenter roughly 258 kilometers southeast of Sarangani, near the Talaud Islands. That placement put the quake effectively inside Indonesian waters, hundreds of kilometers from where anyone actually felt it. Then the numbers changed. As more seismic stations reported in and analysts reviewed the incoming waveforms, PHIVOLCS issued a second bulletin, and this one looked almost nothing like the first. Magnitude 6, 4, a depth of about 13 kilometers, an epicenter just 37 kilometers southwest of Balut Island, in the municipality of Sarangani, Davao Occidental. Tectonic in origin. Intensity 5, strong shaking, reported in the town of Glan. The United States Geological Survey landed in a slightly different place again, magnitude 6, 3, depth around 10 kilometers, epicenter roughly 32 kilometers southwest of Sarangani, with the tsunami threat level set to green. The European Mediterranean Seismological Center matched that 6. 3 reading, but placed the depth closer to 35 kilometers. A routine kind of early disagreement in this part of the world. Put those bulletins side by side and you get the detail that made this event strange before it made it interesting. The epicenter shifted by 258 kilometers between the first and second readings. The magnitude dropped by 0.7 of a point. Both of those revisions are unusually large, and both matter, because the story you'd tell about this earthquake depends entirely on which version you believe. Under the first bulletin, this looked like a brand new magnitude 7 event near the Talaud Islands, a rupture on an entirely different piece of the plate boundary. Under the corrected version, it's a moderate earthquake sitting inside a sequence that's been active since June. Same underlying data, 2 very different stories. Before going any further, it's worth addressing the claim that inevitably follows a correction like this, because the numbers already on the table make it easy to answer honestly. The claim goes something like this. Agencies are hiding the real magnitude. PHIVOLCS published a 7. 0, and then quietly walked it back while nobody was looking. It's an understandable reaction to watch a number swing that hard in under an hour, and in an age where every natural disaster gets picked apart in real time online, that reaction spreads fast. But the reality is straightforward. Automatic solutions get computed from the earliest arrivals at whichever seismic stations report fastest. For an offshore earthquake, with land stations sitting on only one side and open ocean on the other, the geometric coverage gap is enormous, which means the location is poorly constrained along one particular axis. The algorithm will happily place the event hundreds of kilometers off along that axis. And that's a well-documented failure mode in seismology, exactly why the initial bulletin was labeled automatic in the first place. The reviewed solution used more stations, a longer time window, human analysts, and a moment tensor calculation, a fundamentally more reliable way to measure magnitude than the early amplitude methods that tend to saturate on larger events. The revision trail is transparency, not concealment. There's a second layer of confusion here too, and it isn't seismological at all. It's geographic, and it has tripped up nearly every headline written about the southern Philippines this summer. There are 2 separate places named Sarangani in southern Mindanao. The first is Sarangani Province, which sits next to General Santos City in the region known as Sargan. That's the province where the destruction from the earlier magnitude, 7, 8 an earthquake in June, was concentrated. Glan, the town that reported the strongest shaking from this new quake, sits in that province, the second. Sarangani is an island municipality belonging to the province of Davao Occidental, considerably further south, made up of Balut Island and Sarangani Island. This quake's epicenter sits roughly 37 kilometers southwest of Balut. The 2 Saranganis are separated by about 100 kilometers, so when a headline in June reads, "Earthquake hits Sarangani," and another headline in August also reads, "Earthquake hits Sarangani," those 2 headlines aren't describing the same place at all. That distinction matters enormously because the entire question of what this new quake means comes down to exactly where it happened relative to a stretch of fault that hasn't moved in more than a century. And mixing up the 2 Saranganis is exactly the kind of small geographic error that can make an entire online discussion go in the wrong direction. On the ground, PHIVOLCS logged intensity 5, strong shaking in Glan, intensity 4, moderately strong, in Kiamba and General Santos City, Intensity 3 in Masim, Malapatan, Sarangani, and Lake Cebu. Intensity 2 in Banga, Sorala, and South. Cotabato. The USGS estimated a maximum shaking level equivalent to modified Mercalli 6, the point at which everyone in the affected area feels the shaking, objects fall off shelves, and poorly built structures can sustain real damage, while well-engineered buildings generally ride it out fine. The exposure estimates put a human scale on all this. Roughly 15,000 people experienced strong shaking. About 88,000 felt moderate shaking. Around 5.4 million felt light shaking, and another 600,000 or so felt it weakly. The nearest population center to the epicenter is the island municipality itself, home to about 7,500 residents. Glan, 72 kilometers to the north, has around 24,000 people. General Santos, 155 kilometers away, has close to 200,000. It's worth pausing on what those intensity numbers actually describe, because the scale isn't a measurement of the earthquake itself. It's a measurement of what people experienced. Magnitude is a single number for the whole event, calculated from the energy radiated at the source. Intensity is local, and it shifts from town to town depending on distance from the epicenter, the direction the rupture traveled, and above all, what kind of ground you're standing on. Soft sediment and reclaimed land amplify shaking. Solid bedrock doesn't. Two towns sitting the exact same distance from the same epicenter can report completely different intensity levels, and both readings can be entirely correct. That's part of why Glan, 72 kilometers away, logged stronger shaking than several towns physically closer to the epicenter. A reminder that proximity alone never tells the whole story of who feels what during an earthquake. And there's a specific reason that green alert designation might be a little too optimistic for this particular stretch of coastline, something we'll come back to shortly. Here's where this stops being a story about a bulletin correction and starts being a story about geology. When seismologists want to understand what actually broke underground, they calculate something called a moment tensor, a mathematical description of the forces at the source, worked out from the pattern of seismic waves the event sent out in every direction. The moment tensor for this earthquake came back about as clean as these calculations get, at 92% double couple. In plain terms, that number tells you how well the recorded waveforms match the pattern you'd expect from one block of rock sliding past another along a single flat fault surface. 92% is high. It means there's essentially no volcanic signature in the data, no sign of fluid injection, nothing ambiguous about the mechanism. This was straightforward rock sliding against rock. And that reading also answers a companion piece of speculation you may have seen online, the idea that something artificial triggered the quake. An explosion produces a large isotropic volume change signature. A fluid-driven or volcanic source produces a distinct signature of its own. This event shows neither, and its compression axis points exactly where regional plate convergence predicts it should. The geometry backs all of this up. The solution puts the magnitude at 6. 35, at a depth of 11 to 12 kilometers, with a rupture duration of roughly 3.5 seconds. Both possible fault planes dip close to vertical, somewhere around 80 to 96 degrees, which points to almost pure dip slip, thrust faulting, one side of the fault being shoved up and over the other. The compression axis points toward roughly 255 degrees, meaning the maximum squeeze on this section of crust runs from east-northeast to west-southwest. Both fault planes strike northwest to southeast, running parallel to the trench in that stretch. Every one of those numbers lines up with the same conclusion. 255 degrees is almost exactly the convergence direction you'd expect, where the floor of the Sleve Sea is being pushed eastward beneath Mindanao. The trench parallel strike matches too. This is a subduction thrust event, and the data doesn't leave much room for a competing explanation. Now, take the depth and compare it to the earthquake that started this whole sequence, because that single comparison is the most important piece of information in the entire story. The moment tensor places this rupture at 11 to 12 kilometers below the seafloor. The earlier magnitude 7, 8 main shock in June, the one that killed more than 100 people, was placed at roughly 33 kilometers by 5 Oaks and 55 to 57 kilometers by the USGS. That's not a small difference. This new earthquake sits far up dip from the patch that broke in June, meaning much closer to the trench itself, well above the depth range where the main shock's rupture actually lived, which tells you something the word aftershock tends to obscure entirely. This wasn't the June fault surface failing again. It was a different structure. There are two candidates that fit this new event. The first is the shallow near-trench section of the subduction interface itself, the part of the megathrust closest to the trench axis, sitting above and seaward of the patch that ruptured in June. The second is a splay thrust inside the accretionary wedge, one of those secondary faults that branch upward off the main plate interface, cutting through the pile of scraped-off sediment stacked against the edge of the overriding plate. That accretionary wedge deserves a moment of its own because it's the part of a subduction zone most people have never heard of, and it does a disproportionate amount of the damage. As one tectonic plate slides beneath another, the sediment sitting on top of the descending slab gets scraped off the way a bulldozer blade peels material off a road. That scraped up material piles into a wedge pressed against the front edge of the upper plate. It's weak, saturated with water, and riddled with faults that branch off the main interface and angle up toward the seafloor. When one of those splay faults slips, it moves shallow rock very close to the ocean floor, which is exactly the kind of geometry that can lift water and generate a tsunami. The wedge is where a moderate earthquake can occasionally punch above its weight. Both possible explanations are consistent with stress being transferred from the June main shock. Both point to the same underlying story, a different part of the same fault system failing rather than the same patch rupturing twice. That distinction isn't just academic. A stress transfer failure on a neighboring structure is exactly the mechanism by which large earthquakes propagate along a plate boundary over months or years. It is not the mechanism behind a sequence quietly winding down. There's one more thing this mechanism tells us. The June main shock has never been definitively pinned to one specific fault. The two leading candidates have been the Sarangani Trench to the south and the Cotabato Trench to the north, and that question stayed formally open for 2 months. The Sarangani Trench dips west. This quake's solution is east dipping, which supports the Cotabato Trench as the source, meaning a moderate earthquake nobody expected to matter much, just contributed a genuine piece of evidence to a question seismologists had been unable to close since June. The main shock of this new sequence didn't arrive alone, and the pattern of what followed is its own piece of evidence. Over roughly 5 hours, international catalogs logged 8 more earthquakes above magnitude 4. 6, plus a ninth, picked up only by the Philippine National Network, a magnitude 5, 31 kilometers south of Sarangani. A 4, 864 kilometers southwest. A 4, 945 kilometers southwest. A 4, 6, but this one 84 kilometers to the east-southeast. Another 4, 954 kilometers east-southeast. 2 minutes later, a 5, one back at 46 kilometers southwest. Later, a magnitude 5, a 0 at 17 kilometers depth, and finally another 4, 8 back in the southwestern cluster. Read that sequence closely, and something doesn't match the textbook pattern. Aftershocks are supposed to cluster tightly around the original rupture and decay outward from there. The sequence starts southwest of Sarangani, jumps roughly 130 kilometers to the east-southeast, and snaps back to the southwest within 2 minutes. The activity spans a zone of something like 130 to 150 kilometers, rather than concentrating around a single point. On its own, that doesn't necessarily mean anything alarming. A magnitude, 7. 8 rupture loads an enormous volume of surrounding crust, and a broad aftershock distribution is a normal consequence of that. But it's exactly the kind of pattern seismologists note and keep watching, because spatial behavior, not just the size of individual quakes, is the variable that would carry any real warning signal here. 12 minutes after the shaking, the National Oceanic and Atmospheric Administration issued a tsunami bulletin covering Mindanao. That bulletin carried no warning status and no reported impact. The USGS tsunami flag for the event read 0. The more accurate way to describe what actually happened is that the warning system evaluated the event and issued a no-threat product. It fired, ran the numbers, and stood down. That's the system functioning exactly as designed. It's worth understanding why it fired at all, though, because the answer touches on one of the more uncomfortable pieces of physics in subduction zone science. Shallow thrust earthquakes close to a trench axis can generate tsunamis out of proportion to their magnitude. They displace the seafloor across a wide area through relatively low rigidity rock, and they often rupture more slowly, which produces more seafloor uplift per unit of radiated seismic energy than a similarly sized event occurring deeper on the fault. A shallow, near-trench thrust punches above its weight in terms of water displacement. At magnitude 6, 3 to 6. 4, that wasn't a practical concern, and nothing happened. But the very first bulletin said 7. 0 at this exact geometry, which is precisely why the system ran a full evaluation in the first place. Take the same fault, the same depth, the same mechanism, and add just one more magnitude unit, and the entire conversation changes. For a sense of scale, the June main shock at magnitude 7. 8 produced confirmed waves of roughly 1 to 1.5 meters across several coastal areas of Sultan Kudarat and Sarangani. Waves at or below a meter can still be lethal. They're enough to knock people off their feet, sweep them into debris, and pin them against structures. Now, for the part that actually matters, and the reason seismologists spent the day staring at a map rather than a magnitude table. After the June main shock, researchers identified a section of the Cotabato Trench, roughly 70 to 100 kilometers long, that hasn't ruptured since at least the 1950s. And most likely not since 1918. The 1918 event on that structure was a magnitude 8. 3. That's not a model projection. It's a documented recorded event, a demonstrated capability of this exact stretch of fault. The reason a seismic gap like this draws attention has a specific name: static stress transfer. When a large earthquake happens, it does two things simultaneously. It releases stress on the patch of fault that actually slipped, and it increases stress on the surrounding rock, particularly along the fault beyond each end of the rupture and above or below the slipped section. Modeling of these stress changes routinely finds increases of a few tenths of a bar to a few bar in those loaded zones. In absolute terms, that's a tiny nudge. But on a fault that's already spent over a century accumulating stress toward failure, a small nudge can be enough to move the timeline forward. This quake, sitting up dip from the June rupture with a thrust mechanism aligned to regional plate convergence, is a textbook expression of exactly that geometry, a neighboring structure failing because the June event changed the stress acting on it. What makes the gap genuinely hard to look away from is where it sits. It's located between the June rupture on one side and the rupture zone of a magnitude 7, 5 earthquake from 2023 on the other. 2 major earthquakes have gone off on either end of this segment within the past 3 years. The stretch in between has released essentially nothing. Now place this new earthquake on that same map. The unruptured gap sits to the north. This rupture happened at the southern end of the aftershock zone. Whatever occurred that Wednesday, it did not happen on the segment scientists are actually concerned about. That loaded piece of fault is still sitting exactly where it was, untouched. And here's the arithmetic that closes the door on the most common misunderstanding of this whole event. A lot of people hear magnitude 6, 4, and assume pressure was released, meaning the overall danger went down. This earthquake released roughly 1/150th of the energy of the June main shock, on a plate boundary that has been converging at around 7.3 centimeters per year since at least 1918. That's over a century of accumulated slip deficit, which on a locked fault segment adds up to something measured in meters. A magnitude 6, 4 consumes essentially none of that. Nothing meaningful was drained. To appreciate how unusual all of this is, it helps to revisit what the June earthquake actually did. The main shock struck early on the morning of June 8th, local time, offshore of Sarangani province in General Santos City, with a final magnitude of 7, 8, though an early automated solution briefly ran as high as 8. 2. Maximum intensity reached level 8. It was the strongest earthquake to hit the Philippines in roughly 5 decades. As of the most recent official accounting, the toll stood at over 106 dead, more than 1,300 injured, several still missing, and well over 120,000 homes damaged or destroyed. Since then, Phivolk has recorded more than 8,500 aftershocks, several of them above magnitude 6. The largest so far sits around 6. 5. There's a statistical rule for this kind of pattern known as Bath's law, which holds that the largest aftershock in a sequence typically falls about 1 to 1, 2 magnitude units below the main shock. For 7, 8, that predicts a largest aftershock somewhere around 6. 6 to 6. 7, a 6. 5 sits comfortably inside that expected range. This earthquake was the 4th event of magnitude 6 or greater in this sequence, and the 2nd in 3 weeks. A 6, 5 in late June, a 6, 2 in mid-July with an epicenter about 19 kilometers from this one, and a 5. 1 near Balut Island in early August. None of that is unusual for this stretch of plate boundary. 17 earthquakes of magnitude 6. 5 or larger have struck this region in the past decade alone, 7 of them above magnitude 7, a frequency that would be considered alarming almost anywhere else on the planet, but is treated here as simply the background rhythm of living on an active plate boundary. This is one of the most seismically active margins anywhere on the planet, and taken on its own, this event is genuinely ordinary here. What isn't ordinary is the state of the buildings sitting underneath it. Officials stated that no damage was expected from the shaking, and that assessment is calibrated against structurally sound construction. But across the corridor, the June earthquake already battered masonry that's already cracked and weakened, and well over 120,000 homes are already damaged. A magnitude 6, 4, shaking intact walls, and a magnitude 6, 4 shaking walls that have been barely holding together since June are not the same event. This context also explains why officials responsible for the region keep issuing warnings that sound bigger than any single earthquake. Five Oaks has stated publicly that areas along the country's 6 active trenches, the Philippine Trench, the East Luzon Trough, the Manila Trench, the Negros Trench, the Sulu Trench, and the Cotabato Trench, could each experience earthquakes up to magnitude 8. 2. That statement came directly after the June rupture, not before it, which is worth sitting with. It reflects a broader point seismologists have been trying to communicate for years, that one large earthquake releasing stress on one fault does not mean the surrounding region has become safer. If anything, the opposite can be true, because stress redistributed by a large rupture has to go somewhere, and it often ends up loading the very structures sitting closest by. So where does this leave things? This earthquake wasn't dangerous on its own, and it isn't the scenario anyone is actually worried about. Its real value is diagnostic. It confirmed that the crust beneath southern Mindanao is still actively adjusting 2 months after magnitude 7. 8. It confirmed that the structure failing now sits up-dip of the June rupture rather than on top of it. It added real evidence that the Cotabato Trench, rather than the Sarangani Trench, is most likely responsible for the June main shock. And it confirmed that the segment carrying over a century of stored strain did not move. The observation that would actually change this picture isn't a bigger magnitude number. It's a direction. If aftershock activity keeps decaying the way Omori's law predicts, with the rate falling off roughly in inverse proportion to time since the main shock, then this sequence is simply doing what sequences normally do. But if the clusters of magnitude 4 and 5 events start stepping progressively northward toward that unruptured stretch of the Cotabato Trench, that's an entirely different observation, and it requires no new science to spot. It only requires watching where the dots land on the map. Nobody can put a timer on the loaded segment. Earthquake prediction remains genuinely impossible. Fault behavior is only ever identifiable in hindsight, and the section of fault could release in a decade or in a century. Anyone telling you otherwise is selling something. But the honest version of this situation is more unsettling than any theory about hidden data or concealed numbers. The loaded piece of the Cotabato Trench is publicly documented, openly discussed among seismologists, and completely untimable. It did not move that Wednesday. That's the entire finding, and it's worth checking the map again. If there's one thing worth carrying away from all of this, it's that a headline promising something bigger is coming isn't quite telling the truth. And neither is a headline promising that the danger is past. The honest answer sits somewhere in between, in the patient, unglamorous work of watching a map, tracking where the small earthquakes land, and waiting to see whether the dots start walking north.